Today, our topic is structural isomerism. So, what is isomerism? Isomerism is a property in any molecule. Iso means same. Mer means molecular formula. So, the compounds having same molecular formula are called isomers. So, there are different compounds. They might have the same number of atoms, but their arrangement their connectivity might be different. So such kind of compounds are called isomers. They have same molecular formula but different structural formula. Now, for example, let's take pentane. This is N-pentane. Its molecular formula is C5H12. Right? Now, let's take another compound like this one. 2-methyl-butane. Now check for its molecular formula. You have CH3, CH2, CH, CH3, and then CH3. So you have 5 carbon atoms and you have 12 hydrogen atoms. So these both have the same molecular formula, but the structural formula, the structure is different. Now, there are some compounds like this. So here, the both methyl groups around this carbon-carbon double bond are in opposite directions, but here they are on the same directions. They have some slight difference in their properties. This is called cis isomer, this is called trans isomer. These are called geometrical isomers. So the spatial arrangement might be different or the connectivity might be different. So such kind of compounds are called isomers. Now let's see type of isomerism. So what are different types of isomers? So the basic classification of isomers is into two types: the structural isomerism and number two is stereoisomerism. So structural isomerism is where there is different in the connectivity. So the atomic arrangement, like if there is a chain like this, A, B, C, D, and you are connecting it like this, such kind of isomerism is called structural isomerism. When we talk about stereoisomerism, the spatial arrangement, like now I can write ABCD like this, or I can write ABCD like this. The basic idea behind stereoisomerism is tetrahedral shape, tetrahedral geometry. Let's talk about stereoisomerism later. Now, structural isomerism is classified into 5 types. So you have chain isomerism, positional isomerism, you have functional isomers, you have metamers, metamerism, and then you have tautomerism. These are different types of chain isomers. Sorry, these are different types of structural isomers. Stereoisomers are further classified into two types: configurational isomerism and conformational isomerism. So conformational isomerism is because of rotating of atoms around free sigma bond like this. This is called Sohor's representation. So this is rotating in one way and this is rotating another way. Because of this rotation, there are different kinds of isomers formed. There are partially eclipsed, staggered. You have complete like you have different types of conformers. And configurational isomerism is like this. The spatial arrangement is different. So two types: geometrical isomerism and then you have optical isomerism. These are two different types of configuration isomerism. Now, we get, you can see a good example here. Now here, what are conformations? Here, because of rotation. Now see, this dog has rotated like this. So this is an unstable isomer, but this is a stable isomer. Now see here, when we are talking about configurations, in configuration isomerism, you have to break bonds and place it somewhere else to make a new isomer. Now, like this, let's take an example. Um, yeah, H, Cl, and then Br. Now, I'll take a mirror image. What will be its mirror image like this? Br, nitrogen, CH3, and then chlorine. Now, if you are trying to superimpose both of them, they are not going to superimpose on each other, because here you can visualize this using the 3D structure of a tetrahedral atom. Now you have to break this hydrogen and place it here to get this structure. So such kind of isomers are configuration isomer. You can see here the tail is removed. Sorry, the tail is removed and kept in the place of leg, and leg is removed and kept in the place of tail. So this is called configurational isomer. Okay. Now let's see. Let's continue with structural isomerism. The first kind of structural isomerism is chain isomerism. So chain isomerism is compounds. What are chain isomers? Compounds having same molecular formula but different arrangements of carbon chain. Now let's take an example of butane. So this is N-butane. Now if I attach the methyl group here, this will be 2-methyl propane. See. So let's see the molecular formula. If they both are having the same molecular formula, you have C4, CH3, CH3, 6, 10, C4H10. And here 3, 3, 3, 9, 9 plus 1, 10. Yeah. C4H10. Both have the same molecular formula. Let's say pentane. So this is N-pentane. So this is 2-methyl butane, or it is also called as isopentane. And then this is neopentane. You can clearly see that their molecular formula is C5H12. You can check them. So these three are chain isomers. The key idea you are searching behind chain isomerism is they have different parent chain, or the number of carbon atoms in the main chain are different. Now see here, in the main chain, while in IUPAC naming you have seen there are 4 carbons in the main chain, but here you have 3. The root word is changing, so it would be chain isomerism. So here you have 5 carbon atoms in the main chain, here you have 3, and here you have 4. So this is chain isomerism. You can try by yourself by writing isomers of N-hexane. See, now the next type of isomerism is positional isomerism. So positional isomerism, the name itself suggests what kind of isomerism it is. So positional isomerism, they have the same molecular formula, they have the same carbon chain. Unlike chain isomerism, they have the same carbon chain, and the position of, so you have double bond or triple bond or functional group or The substituent is different. Now let's see an example. Now, this is butanine or butene. This is 2-butene. Okay. So here the double bond position here is between 1 and 2 carbons, and this is between second and the third carbon. So the position of double bond is different. So these two are positional isomers. Now you can make like this also. This is also a positional isomer. See, like this. And yeah, let's see the case of functional groups. This is butanol, the hydroxy functional group or the alcohol functional group. It is on the first carbon. So it is 1-butanol or just butanol. Now, if I keep it here, it becomes 2-butanol. You can't place it here and make a new isomer because it will again be 2-butanol. The naming, the numbering of carbon atom we have seen in IUPAC nomenclature. So 2-butanol. The position of the functional group also matters, and this contributes to positional isomerism. Now, let's see the case of substituents. So you have 2-chlorobutane and 1-chlorobutane. So even substituents also result in positional isomerism. So this is positional isomerism. And positional isomerism have different physical properties. They have different physical properties, but they have same chemical properties. There is an important point. No. Functional isomerism. This is one of the most important aspect of structural isomerism. In functional isomerism, we see that the compounds have the same molecular formula. They have the same molecular formula. All isomers have same molecular formula, but they have different functional groups in this case. Different functional groups. How having same molecular formula and they have different functional group? How is it possible? Now let's see. Now, the first case of functional isomerism is alcohols and ethers. We all are familiar with alcohol functional group, which is OH, and ether functional group is this ROR. ROR is ether. How is it possible? Now let me take an example. Now the molecular formula I'm choosing is C2H6O. Now what are the possible functional isomers you can write for it? So you can write an alcohol. So you have CH3, CH6. Yeah, the molecular formula is satisfied. And you can also write a ether. Check it. So you have CH3, you have CH3, C2H6O, right? So alcohols and ethers, they both are having the same molecular formula C2H6O, but here there is alcohol functional group, but here it is ether functional group. So this is a functional isomer. Now, the second case is carboxylic acid and ester. Carboxylic acid is COOH and ester functional group is C double bond O O R. Here R dash. This is ester functional group. Now let's see how are these both isomeric. Now let me take the molecular formula C2H4O2. Let's write the functional isomers. Now C double bond O OH CH3 COH. So this is vinegar or acetic acid. Now let's write an ether for it. Double bond O O, and then you can write CH3 and leave a H here. See. Now ester and carboxylic acid both are showing functional isomerism. Now the third case of functional isomerism is aldehydes and ketones. So aldehydes are C double bond O H R, and ketones are prime C double bond O. These are ketones, these are aldehydes. Now, let's see an example. Let's take the molecular formula C3H6O, right, C2H5, C double bond O, O, H, sorry, uh, H. Check out for the molecular formula, it's seen, and C double bond O, CH3, CH3, C. Both are showing functional isomerism. Aldehydes and ketones also show functional isomerism. So they also show functional isomerism with enols. What are enols? They have a double bond and they have a OH functional group. So let's see enol, right? So let's take CH2, double bond CH, OH. Check this. So you have C. Yeah, now check this. CH3, 3, 4, 5, 6. There are 6 hydrogens, 3 carbons, and 1 oxygen. Yeah. So this is an enol. So aldehydes and ketones and enols also show functional isomerism. And uh, there is another example of functional isomerism. There are many functional isomers possible because there are in number of functional groups. So we have to discuss very less of them. So we have cyanides and isocyanates. So cyanides are C triple bond N, and isocyanates are N C, right? So let's take an example. Let's take ethyl nitrile. So CH3, C triple bond N, and then isocyanide, methyl isocyanide, let's take N triple bond C. So you have a plus here, you have a minus here, you have a plus here, you have a minus. So cyanides and isocyanates also show functional isomerism. And then aromatic alcohols. What are aromatic compounds which follow Haeckel's rule and physically they have a fragrance? So let's take phenol, right? Phenol and CH3. What does this mean? So there is phenol and CH3 is attached anywhere here. So that's the representation we are looking here. So these are called cresols. Okay, orthocresol, paracresol, metacresol. Now, these are isomeric with anisols. What is anisole? OCH3. This is called anisole. And then we also have benzyl alcohol, which is also isomeric. CH2OH. So you can see the molecular formula here, C7H8O. You can check it. So this is benzyl alcohol. Okay. So these are also functional isomers. Now, metamers. So metamerism is observed in functional groups with uh, different atoms. Like these observed functional groups with different atoms. Like what do I mean here? So uh, this is seen in ethers, okay, and then it's also seen in thioethers. It is also seen in amines. Now, the definition of metamerism is they have different number of carbon atoms on either side of a functional group. Now, let's see an example. Now, let me take, okay, let's take diethyl ether. This is diethyl ether. Now, I can also write this like this, right? Check for the molecular formula. So you have C4, CH3, 6, 10, C4, H10O. Check here. You have C4, hydrogens, 3, 3, 6, 4, H10O. See, now here you have two carbon atoms on either side of this oxygen. But here you have one at a side and three at a side. So these are called metamers. They have different physical properties, but same chemical properties. Now, so this is methoxypropane, right? And you can see the same in case of thioethers, right? So let's see in case of thioethers. So thioethers are having sulfur. So you can write this like this. These are thioethers. And then you can also see in amines. So in case of amines, you can write like this. CH3, CH2, NH, and then CH2 and CH3. Okay. This is a diethylamine. And then you can change it like this. CH3, NH, CH2, CH2, CH3. So amines are also showing metamerism. And then amides also show metamerism. What are amides? Amides are R, C, double bond O, NH. These are called amides. You can see here you have different carbon chain. Here you have different carbon chain, and you can rearrange them to form metamers. So tautomerism we'll discuss in another group, another video. So this is it with structural isomerism. Let's recap whatever we have seen. So we have seen isomerism, the definition of isomerism. We have seen chain isomerism, positional isomerism, functional isomerism, and metamerism. So chain isomerism, they have different carbon chain. Position isomerism, they have different position of functional group, double bond, or substituents. In functional isomers, they have different functional groups, and but they have the same molecular formula. And metamers, they have different number of carbons on either side of a functional group. We have seen metamerism in case of ethers, amides, and then thioethers. So structural isomerism is done. So let's see tautomerism in the next video. Right? Thank you.